So this particular one was both the anagram and this crossword I made with the program Crossword Compiler, which is a very good program. So on Texas Hold'em, I'll need 5 volunteers to possibly win $50. Oh, no, I'll make it $10. So I've got a deck here, a deck of cards, and this deck is basically in that order. And I'm going to cut the deck. I'll just keep cutting it until everyone is satisfied. So there's a cut. Another cut? Sure, I'll do another cut. And I have no idea what card will be the one on top here. And then I basically deal out six players. So that's 2 cards to each person. And then I burn the top card, whatever it is, and I lay down what's called the flop. Then burn the top card again, put down 4th Street, which is a single card, burn the top card again, and then the 5th card, the river. And my claim is that my hand here, with 2 pair, I believe, will beat all the other hands. This is nothing. Pair of queens. Pair of 4s. Nothing. And pair of aces. So my 2 pair wins. And basically the way this deck is set up is the dealer will always win. And this was found with a big computer search. Ben Jaffe found different solutions for all sorts of different, so you can basically make any position win for any number of players. And I burned a lot of cards there, so let me play a video of me burning something else. I was going to do that here, but these fuses are like rockets, and they make a lot of smoke. So imagine the room filled with smoke at this point. Yeah, it's off by 5 seconds. But fuses are terrible for keeping time. So how did Jeff Erickson find this? Well, he used a computer. So the shortest amount of time over 0 minutes is 30 seconds, and you can do it with this. The shortest time over 1 minute is 9/8, and you can do it with the diagram I just demonstrated here. Here's the one for the shortest time over 2 minutes, and it's 2 minutes plus 1 over 2 to the minus 10. So we've got a sequence here, 1, 3, 10. And the question is, what's the next number? And it's this. So this is 3 minutes plus 1 over 2 to the power of this number. And the next one would be something really, really, really big. Skews number is a really gigantic number used in Ramsey theory, I think. But 10 to the 10 to the 10 to the 34th. So this next, for a simple recreational math problem, the shortest amount of time you can measure with 1 minute fuses over 4 minutes is a truly gargantuan number. One thing, when you're doing these computer searches and you're trying to find out whether somebody's looked at it before, a great place to start is oeis.org, the online encyclopedia of integer sequences. Here's what that looks like. So if anybody found this particular number, they would know that this has been looked at to some extent. And here's another example from OEIS, the no 3 in a line problem. Now, this problem hasn't been looked at in 15 years. And here's the largest known solution. This is a 52 by 52 board, and there's 2 marks in every single row and column. And if you go any direction, any diagonal or any night diagonal or basically any direction at all, there's no case where there's 3 in a row. And whether there's a larger solution is unknown. But this hasn't been looked at in 15 years. We've got computers that are thousands and thousands of times more powerful than what Achim Flammenkamp had back in 1996. So this is, if you want to have a chance at making headways in math, looking at this problem might be a good start. Here's an example of a solved problem. Patterson's worms, the best way to look at these, the explanation is kind of complicated. So notice just the colors here. We've got a whole bunch of black ones, a red one, a couple green ones. Basically, you've got a worm crawling around eating sediment. And every time it hits a vertex, it looks to see what the pattern is. And based on that pattern, it will turn in a certain direction. And with that, you have a rule, and you can make different rules for each worm. And there's about 400 different worms. And the question is, what patterns do they make? Let me show a program example here. So this is the program Golly, which was developed by Thomas Rokicki. And I can start a worm here. So that's a fast-growing worm. Let me show this one instead. And you can see that this is a very fast program. So that's generally how they grow. And there was, in 1960-something, 69, there were 7 ones that hadn't been solved yet. And one of them is this one, worm 61. Now the scale here is the number of times down the screen has been shrunk. So we're up to 8 million steps here. Now we've shrunk it down some more. This was run by Benjamin Chaffin at Intel. He had a couple hundred chips that he was allowed to test out. So he stuck this problem on them using a routine for handling grids developed by Thomas Rokicki. So we're soon going to be up to 1 billion steps. $10 billion. And now I'd need a computer 512 times as large to show all the pixels. Now 2,000 times as large. 1 trillion steps. So it takes a while to run something this long. We still don't know exactly what this particular worm does. It's the only one that's unsolved now. But they ran it really hard. That was being Chafin that ran that. And I can show other things in Golly as well. Golly was developed by Thomas Rokicki based on this original thing he did for Patterson's worms. And once he did that, he got a certain amount of cachet in running big computer problems. So he wanted to solve Rubik's Cube, since that hadn't been done yet. And he was able to convince his university to let him borrow most of the university computers for a while. And he was able to get the number of moves down to 26. And that wasn't quite, he wanted something bigger, so he was able to convince Sony Pictures to lend him the entire render farm for Spider-Man 3 for several months. And with Spider-Man's help, he was able to get the number of moves down to 23, or to 22. And that wasn't enough, so he asked Google to lend him all their spare processing power for 3 weeks. And Google has a lot of computers. And with the help of Google, he was able to prove that Rubik's Cube can always be solved within 20 moves. This particular position needs 20 moves, so it's both necessary and sufficient. And speaking of Rubik's Cubes, here's Oscar van Deventer, who recently built a 17 by 17 Rubik's Cube.
Hi, I'm Oscar van Deventer, and this is the Curlicue Cube. And the name is there for a reason. This cube has a lot of gears and moving parts. And last time I tried speed cubing and I hurt myself. So when I'm going to demonstrate, I'm making sure that everything is safe. So I'm putting some gloves on. Okay, now I'm sure that I'm not going to hurt myself. So when you look in detail to the cube, you see it has a lot of gears and it moves like this. And once you have turned it, you can move it in another direction, and then even the third direction or back to the first direction as you like. Okay, so here you see how the puzzle works. This is the Curlicue Cube. Thank you for watching.
Oscar van Deventer is the world's foremost creator of mechanical puzzles. He's made thousands of different mechanical puzzles, and recently, due to the miracle of 3D printing, he's able to take his creations in a CAD system and have them printed in 3 dimensions at shapeways.com. So he's printed out all sorts of marvelous creations. And he's, if you go to his YouTube site, oscarpuzzle.com on YouTube, you can see some of his hundreds of creations. Oh, and this, by the way, his co-developer on this particular one was Bram Cohen, who developed BitTorrent. So let me show you one tool that's very good for solving these sorts of puzzles. This is a free program called Burr Tools. So I can map out the pieces of a Burr puzzle along with the shape I'm trying to fit into. And then I basically set up the puzzle, and then I can have the computer solve it. And that's for this puzzle right here. This is the Gordian knot puzzle. I should probably take my money back. And, well, good. There was 12 solutions found. We'll look at the last one here. And here's the disassembly steps. So this is a very powerful free system. Let me just build a puzzle here really fast. So I've got a well, first I'll do a T shape. We've got a pentomino, a T pentomino, and I want to fit that into a 3 by 10 by 10 box. Oops. And for some reason it's not filling. Well, I'll skip that one. But there's this unique solution for the T in a 3 by 10 by 10 box, and it basically solves that instantly once it's set up correctly. So that's one puzzle. Here's another type of puzzle. What's the largest square you can fit in a pentagon? Well, I'm not going to even bother trying to solve that mathematically. I'm just going to run a piece of code here that will basically place a square in a pentagon randomly. And, oops, let me stop that. I forgot to initialize up here. So I'm just placing the square randomly, and then I'm moving around. And after a while, I will cool things that the amount it can shift around is less. And this is simulated annealing or rattling. And very gradually, the square is going to an optimal solution. So I can have multiple pieces, and I can just set them up in my computer and toss it and have it run overnight. And with programmed rattling, I'll get a very good idea of what the optimal solutions might be. And this is just done randomly. I'm basically using a whole bunch of computer power along with a little bit of clever programming. So there's a number of problems that hadn't been solved before that are related to this. For example, the largest equilateral triangle you can cover with 2 squares wasn't solved until 2009. You'd think that 2 squares covering a triangle would be something we would have solved longer than 2 years ago. But it was a computer solution found by Maurizio Morandi. There was a pretty good solution that existed, and everybody thought, well, that must be the best. But Maurizio had his computer attack these and found there's a whole bunch of things that people hadn't found before. Also, the biggest circle you can cover with 5 squares. There's a famous example Gardner gave for packing 10 circles in a square, and 4 different people proved they had the best solution. And all 4 were wrong. It's historical packing is one of Martin Gardner's columns. Martin Gardner, I'll mention him a little bit later, but he wrote the Scientific American Mathematical Games for 25 years. And I highly recommend you find his books. So here's a whole bunch of these puzzles in one place. For example, covering a triangle with 5 circles. I think I can solve this off on the cuff here. And this is part of the Wolfram Demonstrations project. Demonstrations.wolfram.com, the circle covering puzzle. So that's how to solve this one, but I've got a ton more puzzles. So you can go up to 9 or covering squares or covering other circles. And all of these are pretty tricky problems, but I've noticed most people, especially for the smallest cases, will solve them within a minute or less. Because we're very good at spotting patterns. And for this type of problem, you'll probably be able to solve it faster than the computer can, as long as you've got a good tool like this one. Another thing that's developed a lot lately is computer games. And there's a ton of math involved with every computer game. Anytime you've got the 3D motion, you're dealing with lots of linear algebra to turn things around, vectors. Here are some of the other pieces of mathematics that are involved. So I'm going to show a clip from a program where they've changed the laws of physics to make vehicular friction negative. Let me pull that up here. Oh. It's not a pretty world. So friction is definitely a good thing to have. Gravity is your friend too, to some extent. So that's an example of what happens when you mess around with laws of physics. And there's a lot of impressive mathematics that goes into these games. Here's another thing where predictions are difficult. The Curlicue fractal is pretty much, it's not solved what's happening here. Basically, you'll take a constant and apply a routine to it, and you wind up getting these interesting repeating patterns of various sorts. And predicting what will happen is quite tricky. And basically, this will work for any irrational number. And predicting what the temperature is of an irrational number is completely unsolved. Here's another place where a lot of mistakes have been made, packing a tetrahedron in space. And I have a list here of all the people that got it wrong. It wasn't solved until just a few months ago. And this is the solution. This is the best way of packing a tetrahedra. And here's a larger grid of it. There's been like 5 papers in Nature, a whole bunch of columns in the New York Times, every single one of them wrong. It wasn't until just recently someone figured out a way of solving this using a really good computer system, and a better computer system than anybody else before, because a whole bunch of different research has been done on this just recently. Here's another one that was solved recently, the folding problem. So this girl named Brittany Gallivan wanted some extra credit for math. And the teacher said, well, if you fold something in half 12 times, I'll give you the extra credit. So she got some gold leaf and folded that in half 12 times with a very careful process. And the teacher said, oh, well, I meant paper. You have to fold paper in half 12 times. So Brittany got a 4,000-foot roll of toilet paper, went to a mall, stretched it out at night, and folded this piece of paper in half 12 times. And she got the extra credit. But part of that is she developed an algorithm to predict the amount of loss that the paper would have at each step. And that way she could fold it correctly because she knew what would happen at a future step. And when she developed this sequence and noticed that no one else had used it before, she knew she was going into uncharted territory, because she basically ran a computer system, looked it up on the online Encyclopedia of Integer Sequences, and she knew that she was the first person to tackle this problem. And she was in high school. And as a result of that, I got her mentioned on the Numbers TV show, and then later she was part of a Mythbusters program. Here's another case of folding something a whole bunch of times. So I've got a program here, Beyond, and you'll see that it's 48K in size. And the question is, what can a 48K program do? So let's find out. This is part of something called the demo scene, where everybody has to write a program within tight constraints. And one of the constraints is often you have to write a program within either 48K or 64K, and whoever makes the most impressive program fitting within that tight constraint wins the contest. This is a European phenomena. All the graphics, all the music is computer generated by that 48K program. So that's what you can do with a 48K program. All the music, all the animations, all the physics, the music player, everything else was packed into 48K. And Demo Scene has many amazing programs like this. So let me give you an example of something I've done. There's kind of a Heisenberg uncertainty principle for old problems. Once you've looked at them with a sufficiently powerful computer system, you change their states. So this is one of Martin Gardner's columns, Mrs. Perkins's quilt. And he gives examples for how to divide up a square into smaller squares so that the squares don't have a common factor. So you can't divide a size 6 square into 4 3 by 3 squares because all the squares would have a common factor of 3. They have to have the common factor of all the squares has to be 1. So here's solutions from 1 to 12. He also talks about the fractional squares problem, packing squares of size 1/2, 1/3, and so on into the smallest rectangle. And the sequential squares problem, where you've got squares of size 1, 2, 3, and etc. And in particular at the time, they were able to prove that squares of size 1 to 23 can't pack into a 66 by 66 square. So here's my attempt to update the original problem. I wrote a column for MAA.org called Square Packing. And this guy here ignored the proof from 30 years ago, and he found the solution for packing squares of size 1 to 23 in a 66 by 66 square. Lots of people make mistakes. It's always good to check things. He checked it, and he was the first one to solve the problem. Japanese student. Here's more examples of sequential squares packing in smallest rectangles. No one has solved packing 33 squares into the smallest rectangle yet, or anything above it. Whether there's a rectangle that is completely tileable with sequential squares is an unsolved problem. Here's fractional squares. So this is a square of size 1/2, 1/3, 1/4, and M. Paulus came up with a very good algorithm for solving these. So let me pick a rectangle here, and there's a solution. And this algorithm works in real time. And it basically packs up the rectangle very efficiently. And one I solved myself was the Mrs. Perkins's quilt problem. So here's a 308 size square divided up into a minimal number of smaller squares. And I've got all the solutions up to 1,999. That's a lot of quilts. Part of it is I found there's 16 different growth methods that are really good for taking a small solution. For example, if this is a small solution here, if I take out this 3 and I substitute a 5 and then I put 2 on the wings, I get this solution for a slightly larger square. Or if I just put 5s around it, I get this solution. Or if I divide the 3 into quarters and multiply everything else by 2, I get this solution. And here's 16 different growth methods I can use for growing smaller solutions. And I think I'll skip this part. This is the technique I use. This was not my technique. It was developed back in 1936, but they didn't have supercomputers. So I was able to take their method and program it. Oops. And then I took a look at billions of graphs, or actually my computer did. And these are the counts here. And here's a sample solution where I had to use a two-connected graph for the solution. This is something I still haven't figured out yet. I can look at all the 3 connected graphs. For example, for 20 and 21 edges, the counts are these. But in 2 connected graphs, the counts are these. And that's beyond my computer's ability right now. So I'm not quite sure how to tackle that yet. So I'm not sure I've proved I've got the best solutions. And here's a new problem that I'm not sure how to solve. What's the smallest rectangle you can make out of squares where no 2 share an edge, share a full edge? So here's the smallest one for 9, for 10, for 11, for 12, 13, 14, 15, 16. Here's my best solution for 53, or for 36. Size 36 by 36, I can do it in 53 squares, like so. But I have no idea how to prove this because there's a lot of graphs of order 50, with 53 edges. So I have no idea how I'd go about proving these antiquilts. And no one has really looked at this problem yet. Here's a puzzle based on these. You want to divide up this rectangle into, or the square into rectangles so that the sum going down is equal to the one going across. For example, 15 is equal to 8 plus 1 plus 6. So the first rectangle would be here. Because 15, with this 1 by 3 rectangle here, would be equal to 15 here, 8 plus 1 plus 6 here. And similarly, 15 plus 3 is equal to 4 plus 14. So this square would be another piece of it. And I've got 1,000 puzzles here, or 1,300 puzzles here. And these are all pretty good logic puzzles. Here's the four-color theorem, of course, was famously solved with a computer system at the University of Illinois, which is what I'm right next to. And here's a bunch of different four-colored solutions. One thing that slowed down the four-color theorem for many years was they thought they'd proved it with something called Tate's conjecture. And how that worked was if you take the Hamiltonian cycle of a graph, a polyhedral graph, and that's what this thick line is here, it visits every vertex of the original packing. So this is almost a cubic graph except for the corners. I can throw out the brown, I believe, and take a look at what else is left. And you get this other mapping here. So think of taking this piece here, just cut out the piece that would be within the thick lines, and have that as a blue film. And everything that's within the thick line here, use a yellow film, and then lay those on top of each other, and you'll get this coloring. You'll get a four coloring based on the Hamiltonian cycle. And it was thought that all polyhedral graphs had a Hamiltonian cycle until William Tutt found a counterexample in the 30s. And then the four-color theorem took off again, and it was solved 40 years later. So this is well known. 5 points determine a conic section. This is not as well known. 9 points determine an elliptic curve or cubic. And here's one I haven't solved. Here's an ellipse that goes through exactly 7 lattice points. And here's an ellipse that goes through exactly 11 lattice points. I wasn't able to find an ellipse that went through exactly 13 lattice points. And then I got bored with the problem, so I haven't solved it. But maybe one of you would like to be the first to solve that problem. There's lots of research in primes right now. Here's an obscure problem. Boniakowski said every single polynomial, if it's not obviously factorable, will, if you divide it by the greatest common divisor of f of 0 and f of 1, the new polynomial will generate an infinite number of primes. And that's been unsolved for over 100 years. And these red points here are where primes are on these particular polynomials. no one has made any sort of headway on this particular problem. Here's another unsolved problem. It's possible to pack a square with 45, 60, 75 triangles, but the smallest known solution requires over 300 triangles. And 300 pieces would make a lousy puzzle, so I've been wanting to make a smaller version. But I found this is another tricky problem. The smallest number of triangles is completely unknown. This particular solution here has a flaw here. But all of these are, except for this one here, are 45, 60, 75 triangles. There are cases where you don't want to use a lot of computer power. This is a quote by Jacques Bernoulli. With the help of these formula, it took me less than 8 minutes to find that the 10th powers of the first 1,000 numbers being added together will yield the sum, that big number. From this, it will become clear how useless was the work of Ismail Bilialdias spent on the compilation of his voluminous Arithmetica Infinitorum, in which he did nothing more than compute with immense labor the sums of the first 6 powers, which is only a part of what we have accomplished in the space of a single page. This is one of the most famous papers in mathematics. The Bernoulli polynomials revolutionized a lot of aspects of number theory. But it came about because he was enraged at this person writing a big book of just adding things together. Here's a more recent case of a place where the computation really wasn't well suggested. Here's an example of a Golem ruler. The marks on this ruler all have distinct distances from each other. These are the only distances that are skipped. And here's where the marks are. So Distributed.net wanted to see if they could do a distributed search and find the optimal Golem ruler for 24 marks. So they managed to get 41,000 people involved for 4 years, but the solution they found was identical to the one discovered in 1967 by these two guys. So they used a tremendous amount of computer power to do something that was in the realm of combinatorics. And that's a special case. Once you've used computers enough, you start appreciating some of the tricks in mathematics, some of the special methods, and combinatorics and certain algorithms are really, really powerful. These two combinatorialists were able to do in the space of a couple days what it took 40,000 computers 4 years to solve. So when you're dealing with a gigantic amount of computer power versus a smart combinatorialist, the combinatorialist will always win. Now let me pull up this here. I'm amazed at how fast Fractal software has gotten recently. So I'm doing this in real time right now. Let's zoom out here. Oops, I lost my Mandelbrot set. Oh, it's gone now. It's in there somewhere. Oh, here's another one. So we can, I remember it taking 8 hours for my scan of my Mandelbrot set to render years ago. So this is real-time fractal exploration. Since I did a whole bunch of stuff with the Mandelbrot set in the 80s, this is mind-boggling to me that I'm able to get this picture here so fast, because I remember when it took hours to get the same sort of picture. So, in conclusion, never fully trust that something is too hard or impossible. Find an obscure problem. A good thing to do is go to the local library and just look at anything that's older than the year 2000, which is pretty much everything for most college libraries. Research the problem some, and that means go to Google and type in the words dealing with that problem. It's amazing how often I have to explain that to people. Work out a few simple cases and try to turn it into a sequence of some sort, and then take that sequence and put it into the online Encyclopedia of Integer Sequences. That will tell you how current the problem is and if anybody else is working on it. After that, set up a program and let it run. If you're doing overnight runs, that's going to give you a lot of credence later on, because you know how to set up a computer and have it try to solve something. That's a talent that many people don't have. And then once you've tried that, look for patterns in what you're producing. Improve your program, look for algorithms that can make it faster, and then post your results online. Usually, if anybody else is looking at this problem, once they find any particular number you've come up with, if they find the same number, they'll come right to you and you can collaborate with them. And that's my talk, but let me do one more thing here. I've got a Fractal Zoom that I'll have in the background here. Let me turn that on here. And I'll be glad to take any questions. Well, it's a really good video.
You had a program that was doing amazing things in 48 days. Why isn't the commercial software you buy it with billions of...
Because it's tricky to be efficient. Even Mathematica is a big program. Of course, there's a lot of things that are tricky to do in a small space, and that's part of Turing machines. There are certain like pictures and whatnot. If you want a particular completely random block of 124 by 124, you're not going to be able to compress that down in any sort of appreciable way. So that particular program, there wasn't a lot of randomness except that the randomness that the computer itself generated. If you gave it a picture, it wouldn't have been able to compress it. So there's a lot of things in, say, Mathematica where you have to produce a picture of a cat, and you can't fake it with a pseudo cat that was computer generated. It has to look real. So that's one of the reasons a lot of things are bigger. But the main thing is just it's tricky to be this efficient. Anything else? Now, this video here, already the amount of zooming has been enough to take something the size of an electron and expand it out to the size of the universe. And we're going to loop through that 5 times here. This is one of the powers of computer systems now, is they're powerful enough to make the universe itself insignificant. So this was developed by a team called Team Fresh. They used the program I showed earlier, Fractal Explorer, to go to a particular spot within the Mandelbrot set, and then they let that render for 6 months on their home system. And this movie is the result of all that rendering.
What size bit arithmetic are they?
64-bit. Fractal Explorer has a very good built-in system for multiplying huge numbers together. Multiplying huge complex numbers together. Because Mandelbrot said it's on the complex plane. And at the time, this was the deepest zoom ever done on a computer system. And this was last year, I think. Now they've done a few deeper zooms, but with the same resolution. But I didn't find them quite as interesting as this one. Oh, part of the process, he had to stitch together 500 gigabytes of movies and then compress them down to get this movie into a reasonable size. He managed to get it down to 10 megabytes. Sure. Mm-hmm. So already we've expanded an electron to the size of the universe 3 times. I think we're up to 4 now. The number of particles in the universe is 10 to the power of 100, and we're already past that.
1998, we had John Milner here was giving the spring lecture series, I guess at that time, on some of the dynamics behind the Mandelbrot set.
Did this movie produce any new insight into this dynamical system, or?
Not really, but it sure got a lot of interest in it. This video got, I think, more than 1 million hits on the place where it's saying, and it basically made the news on all the various sites like Boing Boing and elsewhere. So it got millions of more people interested in fractals. And I know Fractal Extremes had a lot of sales after that. As you might guess, they're zooming in on a Mandelbrot set, and there it is. And this is going to disappear very quickly, but that's what they zoomed into there. So thank you very much.